Alright, so welcome everyone to our, seventh lecture. And today's topic is dynamic programming. It's one of sort of more universal tools, much more applicable than greedy programming, greedy approach, greedy heuristics. Now, technical issue is not really an issue, but you're talking about attendance. So there is going to be a attendance sign-up sheet for the next lecture for the data structures class. The administrations, they want a sign-up sheet. So for those, if you have a group chat or something, you might want to let know the people who are running late. So for the next lecture, right? So of course I want to see you here as well, right? But and I'm glad to see you. But if you have a chance to tell the others that the next lecture there's going to be a sign-up. So I don't know what it's going to count for. I mean, I do give some extra consideration for attendance, a little bit, right? But the school actually wants to see the attendance as well. So yeah, so it's going to be the good old sign-up sheet. Okay, but today's topic is dynamic programming. Again, we can use the notebook I made a while ago. We'll talk about the origins of this term first. This guy, Richard Bellman, pretty famous guy, right? Basically a mathematician. And so the story goes, the dynamic programming, well, it's not really about the programming as we know, the regular programming where we write code, because he was not really a programmer, as we know. Programming, he was mostly a mathematician working optimizations. He's basically trying to find some optimal solutions. And the story goes, he was getting money from, I think it was military, American military. I think he was working for Rand Corporation, I believe. It's a big think tank. And the story goes, there was a general or somebody who really hated math or something like that. So he said, okay, dynamic programming, this sounds good. I'm going to sell this stuff I'm doing, right, as dynamic programming. You know, that's just a good, some terms. Nobody knows what this. I just invented this. Right, so they can object I can do whatever I want basically, right? And he came up with some cool stuff afterwards. But it turns out, so programming in this sense is meant actually as like a TV remote programming, things like that, actually like a television programming. But of course now it's applicable also to regular programming. And so what's the essence of this whole approach? Well, it's something we use for those who have programmed before, use all the time. Basically we store some results and use it for future, or in other words, caching results, caching some calculations and using them for next for the solution. So again, typically that means we have some sort of state. We are going to be storing some state, and well, in the classical dynamic programming, we're going to be building up this solution space. We start with a simple solution and keep building up. Right, that's the usual case. But also, we will see today that it's also possible to work the other way. Use basically, which is even easier. Basically, the caching approach is you start basically using a regular recursive solution, which might be bad, like a full search. But if you cache the results, meaning you don't look up you don't do the same thing again and again. You have somewhere memory. You save these results. You can gain a huge efficiency. Basically, sometimes you can go from exponential complexity, you can go to linear or quadratic complexity, or maybe even linear, even log linear complexity. So, but the approach is simple. Basically, it's simple on paper, right? You save some results. Basically, that's the whole idea, right? You pay with memory for time. You're sort of trading memory for time. Also, a very common approach in programming, in solutions, trying to find a solution. Can you save some? Can you do some work before? Can you use some existing work? Can you basically trade this memory space for time? And oftentimes it's possible, right? So, okay, so basically here the program is making a set of choices, right? And dynamic, that was just he came up, right? Has nothing to do with dynamic data types, things like that we know in programming language theory. Right, here dynamic means just things change. That's all it is, right? So it's basically like a big field, right? So the core technique is basically let me make this a little bigger, yeah. So you decompose your problem, this recursive solution, and maybe, hopefully, right, there is some overlap between these sub-solutions, sub-problems. And if there is, then it's very possible dynamic programming is going to be one of the answers. Again, dynamic programming is very popular in programming Olympiads. Again, again, the job interviews, high-level interviews, again, because it's relatively, well, it sounds very simple, right? And I think you'll, from today's lecture, you will see that it's not that hard as far as the concept, but implementing, if you have a completely fresh program, like a problem you never seen exactly the same problem before, is relatively hard, right? Because you have to think of what could be a good sub-problem, right? What do you save? What kind of information you save, right? So today we will look at both ways of approaching it, bottom up, right? Starting from simple problems, or maybe just start from the top, actually. And both ways work, actually, right? So, memoization, not memorization, but memoization, a concept, basically, right? So this means using a cache to store some previously calculated result, basically, right? Again, memoization, well, of course, in some ways, it's very similar to just regular memorization, right? So caching also, I would say, is very, very similar term. Okay, so we'll start with, again, the little puzzle, longest increasing subsequence, which is kind of silly puzzle, right? Good morning. Hi. Right, so, good morning. Okay, all right, very good. So we have a good turnout. Like I was saying, next lecture there's going to be a sign-up sheet, so very good. So almost everyone's here. Yeah. So we're talking about dynamic programming. Now this puzzle, I'm trying to find actually, I don't know where actually would you use this, maybe for some DNA analysis or something maybe, or some sort of, right? But you have a longest increasing subsequence. So again, when it keeps going up, right? It keeps going up or stays the same, the numbers here in this case, right? So here you have 1, 2, 4, right? And that will be one solution. What's the other solution here? This one also, right? Yeah, you have basically 1, then 0 doesn't count, you just ignore it. 2, 4, that's one solution, right? 3, well, 3 is not a good starting point, because you only have 3, 4, that's not a good solution, right? You're not allowed to go down. You can stay the same level, basically, right? So, is 1 to 4 and 0 to 4, right? So, that's your list, right? And I'm going to use a combination, since I'm lazy. Okay, I need to sign in, of course, to my, cancel, no, cancel this. I need to sign in, yeah. Right. Hopefully, I remember my passwords. Okay, yeah. So we need to connect the machine. Since I'm lazy, I don't want to do the combinations by myself. I'll let the standard library from Python do the combinations for me. Right? It's pretty nice, nifty standard library submodule. And of course, I have my list, right? So I can, for example, use combinations. Say, okay, 3102, 3104, 3124, right? And so all I have to do is now I have my combinations of length 4. I need to check whether each member, does the increase. Is it sorted? Basically, in other words, is it sorted? And we already know how to do that, right? You just check the pairs, right? Easy stuff, right? Check the pairs one by one, right? And it's at least equal, less or equal. The first one is less or equal to the second one. Of course, then it's sorted and it's actually increasing, right? Or how should I say? Not increasing, but not decreasing. I should say it like this, right? There's actually a specific term for this, right? Monotonically increasing, I guess that's, I think, the word term. Okay, right. So, and again, how many of them are there, right? If you have a length of 5, right, you only have 1, right? Length of 4, right, 3102, 3104, right, yeah. But how about 3? Right? 310, yeah, that makes sense. 310, then 312, 314, right? So all I have to do is check all of these, right? And if I find one which is sorted or not decreasing, so then I have my solution, right? So yeah, a side question or a side quest here is how many of these choices are for 3, right? And here I'll actually show you a little cheat sheet. It's a formula for, and now I'm going to mess up, not permutations, but basically the formula is factorial, so it will tell you exactly. You have like, so pick 5 out of 5 is just one way, right? Pick 4 out of 5, there's 5 ways of doing it. Then 3 out of 5, you have 10. Same goes for 2 out of 5, right? And then you have 1, you pick well, only one item, 3, 1, or 0, 2, 4, right? Tuples. And obviously you have 0 ways of picking 0, right? So, again, this has a relation to something called Pascal's triangle. Maybe you've probably heard this term, right? And we'll see later how to build this, right? So it's interesting how there's different areas of math actually overlap here, right? But okay, but that's actually not, of course, our main subject. But what we are going to do is our naive solution. I'm going to actually add this in text. Naive solution to longest how did I say it? Increasing, right? Longest increasing, right? Or no, longest increasing, non-decreasing subsequence, right? So, basically, right? And this is really easy to say. So, for length in range, you start with maximum length, right? 5. Hopefully, it's already sorted, right? And of course, here I'm extremely lazy, right? What I do is, if I create these combinations, but they are given as a, how should I say, they don't give you, as is usual for optimization purposes, they don't give you a list, right? They give you what I call subresults in Latviski. It's a generator, I believe. It's a basic iterate. It's iterable, but it's not actually a data structure yet ready to be given to you, right? So that's why I create a list out of it, right here, right? So to create an instance, a list instance, and also I sort, right? Which of course also gives you, well, in this case I guess it gives you a tuple, I guess. But most likely, at least it doesn't matter, we can compare it, right? So here, if they are exactly the same, right, that means this is a lazy way of checking if it's already sorted, right? Of course, this is, we could have checked, you could optimize this part. Why? Because this part, okay, let's look at this part here, right? This part here, what kind of complexity is hidden here? In this part here, in this line?
N log n.
Yeah, n log n, because we know sorted is Tim sort, so technically it's n log n, right? Because we keep sorting all these sequences, right? We could have done this in linear time, right? Checking pairs is faster actually, right? So this is technically, right? Since again, this is just lazy, quick and dirty solution, right? I could do fix me. Other fix me could rewrite this in linear time, right? But that's of course not the problem here, of course, right? Because what we have, so let's look at this complexity of this, right? So we have, well, first of all, let's see if this works, right? Before we check the complexity, see if this actually works. This still works, right? So naive list, 3, 1, 0, 2, 4, and I find the solution 1, 2, 4, right? And I could, of course, right, find another one. Let's check another one. Let's say naive list, right? And let's do something like, I don't know. I'll just do something. I don't know what it, right? And obviously, doing these random numbers, right? So, okay, I don't know what the solution is going to be. It's probably going to be like 1. I don't know, 1, 2, 3, 6, 7, 8, 93, probably, right? You know, it seems a pretty simple solution here, right? So let's do it. Yeah, so 1, 1, 1. So 1, 1, 1 counts actually, 1, 1, 1, because it's not decreasing, right? 1, 1, 1 counts, 2, 3, 6, 7, 8, 9, 93. Okay, it looks right? You do all these ones first, right? Then you do 2, 3, 6, 7, 8, and 93, right? Okay, yeah. Now, again. So this works, right? But the problem is, of course, is complexity, right? So, okay, we already know this is n log n, right? Each time, but the problem, that's not the biggest problem, right? Because we have outside, we have 2 loops, right? Okay, this loop is pretty simple. So this would be what, linear, right? Of course, length of the sequence, right? Length of the sequence, because you just go through checking, right? So it depends on how many items you have, right? 50 items, you have a loop of 50 items, right? So if we didn't have this loop, right, inner loop, right, we only had this and that, that would be n times n log n, so n squared times log n, roughly, right? But alas, unfortunately, things are much more complex here. Unfortunately, the big, or the heavy hitter, so to say, is hidden here, right, the combinations, right? So, and I only gave you a hint, right? This is basically complexity is ridiculous, right? So it's something like, so, and factorial divided by k factorial n minus k, right? And well, the thing is, of course, for some large numbers, right, of course, this factorial is going to dominate because this smaller one will be relatively small, right? So you have 1,000 items, right? If you have 1,000 items, right, somewhere in the middle, the number is going to get pretty huge, right? You have to pick 500 out of 1,000, right? That number is going to be pretty big, right? So now I'm not sure it's actually going to reduce to a factorial complexity, but again, if you have n times something which is close to factorial plus n log n, right, this is going to get pretty bad pretty quickly, right? It worked on like 10 items, right? But if I do some random ones, right, let's see, C 2024, right, it's still on 2024, right, and we can, it works, right, but it's microseconds, so not too bad actually. Or 500 micro, okay, because this is now on a Google. Last time I did on my own computer, so Google's slower. Yeah, and 20 is already entering into, should be getting to a second territory, so probably like a second, or 580 milliseconds, that's half a second. So to find the longest increasing subsequence for 20 item list, you need 500 milliseconds. So look at this, we went from 10 went from microseconds, so 500 millions of seconds, so half a thousandth of a second, right, to 1/2 a second, so 1,000 times slower just by going from 10 to 20, right? So again, hopefully you agree that going to 30, we're not going to try going for 30, right? That's probably going to be about 50 seconds, maybe? I don't know. I'm not even done. You can try it? I think I tried 25 here, and that was, well, I guess we could try. Let's see. I'll do time, just single time. I'll do it one time, right? I don't know. Feeling, yeah. Let's do this. I think this one will work. A single percentage sign. So I'm thinking, I don't know. Thinking bad. Yeah. Okay, 23 seconds. 23 seconds to have 25 items, right? So, yeah, it looks like the solution looks good, but again, of course, right. So, this again leads to the problem, right? How brute force, right? So, in general, yeah, you start with the brute force. Again, you have some unknown problem. See if brute force works. I mean, maybe this naive way of looking at all solutions, right, which we are doing, maybe that's sufficient, right? If you only have 10 items, right, you don't really need anything fancier in practical terms, right? But of course, you probably have more items than that, right, in your problems, right? So we will look at finding, having some help, right? So we'll go back to our friend Fibonacci, right? So Fibonacci, again, I think we used this in data structures class. I wrote this recently. I know I wrote it recently again, right? So let's do a recursive solution, right? Which is, of course, if it's less than 2, right, it's 1, right? So first two numbers are 1, 1. Afterwards, it's you combine, of course, the previous and the one before, right? Right. So this is interesting solution actually. If you think about it, right, it's completely recursive. So only we define the base case, right? Classical way of, well, a recursive solution, right? And hopefully by now you know what the problem is, right? Right. The problem is here, right? Yeah, the problem is here, right? 1, 1, 2. It works, right? Seems to work, okay. Right? We get 8, yeah, okay. We get 10. 10th item, right? Not 10, but 8. It looks okay, right? So let's do 1 to 15, right? And for fun, I also, for those who don't know, of course, Fibonacci numbers, each their limit, right? As you approach infinity, they go towards something called golden mean, right? There's the shell, right, and it's everywhere, right, in the nature, right. So the golden mean on the limit, I think, something like that. It looks like. So if you calculate enough Fibonacci numbers, you could calculate the mean. But of course, also there's other formulas. It's actually you don't need to use Fibonacci numbers for it. It's just the way they do approach that. So. But yeah, so it looks like the program works. It looks fast enough. It was actually 0 seconds still, okay. So we got up to 15 up to 14 actually, right? but it works, right? So yeah, so that's the Fibonacci golden ratio, right? Keep going up, right? Of course, there's some talk I read about not all shells follow this pattern. I don't know, not all seashells do that, but okay. But now let's see what happens with our solution, right? So 0 seconds, still good. 35, I think we'll still start getting problems. Yeah, you see all these calls. Okay, we still got solution, but it took 4 seconds. So I already know up to 30, our program still works okay, right, on a normal computer, right? But getting Fibonacci of 35, of course, I mean that's already getting silly. 4 seconds, that's unacceptably slow for this type of problem. So what do you want to do? Okay, so I could do also, well, I could do 36. If it's not, I think I'm going to probably not stack overflow, but recursion limit might be exceeded. Okay, but we can do it. Maybe, so I expect it's probably going to be like 10 seconds or 15 seconds, probably, right? You can see all these recursive calls going on right here. 7 seconds, okay. Not great, not terrible, right? But, but it's getting worse, right? So, and this is a stack overflow actually answer, and you can see what's happening, basically, right? Even I call Fibonacci 7, right? You can see this in back, right? You see it here also, right? I hope, right? Right. So, Fibonacci, when you call for 7, you don't know any answers, and you do. But what you do is, of course, you call it recursively on 6 and 5, right? And of course, eventually you get down to 1 and 2, and we do now answers for 1 and 2, which is 1, 1, right? This 1, 1, basically, right? So, what's the problem is? The problem is, of course, this certainly looks like, well, exponential growth to me, right? You keep going, right? This 3, right, keeps growing in both cases, right? So, one side is 6, 1, 5, but it keeps growing, growing, growing. So this looks like 2 to the n complexity, possibly because it's going to be increased like almost, well, we add 1 item and we almost doubled the length, right? It smells like almost exponential complexity, right? So pretty bad, right? Again, big old cheat sheet, right? And we know 2n is up there with the really bad one. Not as bad as factorial, but pretty bad, right? So, and again, so now this leads us to the big idea of this top-down approach, right, of memoization, right? So, if you think about it, the basic idea in this solution is, if you see that if you suspect your recursive solution is doing the same thing over and over, then you have a really, a free win or cheap win optimization, this dynamic programming approach. You basically add some sort of caching, right? You check whether this result was done before, and that's all, right? So, what do we use for this type of, what can we use for that actually? Well, what kind of data structure? Array would be okay, possibly. Array may be here as well, but in general terms, you probably want to use what Python calls dictionary, but other languages use hash map or map, because of the property that you have O1 time of checking whether something exists or not, right? So, again, we'll talk about data structures. There's underneath the hash map, there is an array usually. It's implemented as an array, but specific way, right? But that's a different story for different time. But you have this O1 checking time, right? So you don't lose any time checking whether this exists or not, basically. It's constant time. Whether you have 1,000,000 items calculated or only 3 items calculated, right? So you insert this check, right, which is fixed time, and you gain this huge increase in speed, right? So the book, which is on a Python algorithms, of course, it creates its own memoization function, which is maybe taking things a little bit too far. You don't have to, I'll give you a hint, you don't have to do this yourself. It's already built in Python, many other languages too, but the idea is this. We have a wrapper, basically. We're going to do a wrap. We're going to take a function, right? This is page from functional programming, right? We're going to pass, we're going to give our function to this memo function, basically. So it's called, we define something called memo. We create a cache, right? And we pass some function, right? Whatever it is, probably it's going to be our Fibonacci. We're going to pass it in, right? Right? And then we define this wrapper, right? And we return the wrap, basically, here, right? This looks like closure actually, right? So O1 cache, right? We check, right? On return, right? So basic idea is this: if we have not already calculated, if it's not in cache, it's a key. So keys are going to be the function arguments, right? We check whether they are in or whether they are in our cache. If they're not, we return it. And again, this takes advantage of this closure. Again, this is this concept that this cache stays within this function. Again, it looks a little bit tricky here, but again, the good news here, of course, you don't have to do this. You could do this already for inside the Fibonacci function itself. But let's see if this works actually. And if I remember correctly, it might not actually work correctly. Right? We pass it, or maybe I'll restart my function. Let's see. So I pass it. Right. Yeah, it seemed to work, but I didn't get fib memo, right? Yeah, I don't think actually we'll get. I think it's going to be next time. It's going to be faster. This I think. Yeah. So it sort of works, but doesn't work completely correctly here, right? So now it works. Right? Basically, it knows that it has the cache built in, basically, right? It still doesn't work with 40, right? So. Let's try it one more time with the Fibonacci, a new FibM, right? Let's see if this works. Oh yeah, I think now it will work. Let's take a look. Yeah, now it works instantly, right? Yeah, correctly. I think there was, ironically, there was some caching issue with the code itself, right? So I think it was using the old Fibonacci function here. So what I did is here, I made a new Fibonacci function, basically just copy, basically, right? I've wrapped it. Right, this is Python decorator. I don't know, they probably didn't teach you decorators in a Python class, right?
Not really.
Yeah. So basically what it is this is basically we are passing this function we just made to this memo function, basically. We're passing it as a parameter here. That's what it means, right? So, and it's a really, really concise way. So we are giving a function, another function, and we are getting back a new function. So basically, this function is being modified with this caching, basically, right? So this is a relatively advanced concept as far as Python goes, right? But the idea, again, is using this syntax, we get a basically almost free win, right? So right now, by keeping our seemingly incredibly simple and I would say almost naive solution, right? By adding this decorator, we gain instant speed up, right? 35, it should work also for 38, right? I hope so. Yeah, you see? That nanoseconds, right? Because the cache is already full, right? So all it has to do is, I keep going up, right? It does not have to calculate these first 35. It only has values inside the cache. So pretty cool, right? So I think I'm going to do 45. I think I can do it. I think I can do it, yeah. Basically, you see, almost, so only have to calculate like 7 more items, basically, right? So the cache is already full, built in, right? So, but again, in order to do this yourself, you have to read, of course, you have to learn a little bit about decorators, you have to read about functional programming, you have to read about the idea of this, right? I think the idea is kind of clear, but the idea of you have a function which takes a function and returns a new function, a wrapper function. Yeah, it's a pretty powerful concept, basically, right? So you give in some function, and you get back another function. This concept, actually, where else will you use this? Let's say you have a function which does something, right? But you want to add logging, for example, right? So you could add this, instead of caching, you could say, okay, print to some log file or something like that, right? And you pass any function, and you'll get logging for free, basically. That's another way of using this wrapper functions, basically, right? So, okay, but let me show you the good news before we go to the break. We still have some time, right? Let's see can we do this? Yeah, fast, right? That's our limit, 3,000, right? Yeah. So I can do this. Yeah, no problem. All right. Let's do 10,000 again. Our old friend. Or will it work? Yeah, it still works. 2,000. Yeah, so a pretty big number, right? 5,000, can I do 5,000? I think I crashed. No, I still do it. Okay. All right, that's good. Okay, but here's the good news. We did this all by hand, basically, right? Python has this built in, this caching. You import functional tools, right? And there is something called the LRU, And LRU stands for least recently used caching. So what's the idea? There are different ways of caching. What's caching again? Remembering something done, right? So LRU, least recently used, meaning we store the items we used recently, right? So you have like, you did calculations for 1,000 different values, but your cache size is only 600. You remember the last 600 you did, right? The order doesn't matter, but actually the order of how you approach the problem matters. Well, here, since I assume we have enough memory, right? We have 12 gigs of RAM, right? We're not gonna do like, I don't know, 10 billion items, right? So max size none. But the thing is, yeah, and it's another thing is, I think default was 128. Last I checked. Maybe it's now a little bit increased. Maybe it's, you have to read up, of course, this cache replacement policy. Of course, you read more on this instruction. But basic news is this: you need only these two lines. You have a recursive solution in Python, right? Import functional tools, import this add the decorator. So basically what this means is you are wrapping your function with this caching function basically inside, right? So basically all this work we did here by hand, right, which looked kind of fancy, maybe there's some inefficiency, right? This is how you had to do it maybe 10 years ago, right, before they added this caching built in. So this is a really nice feature of Python, actually, right? So you have basically this built in, right? So cache everything, and now, yeah, there's also actually a newer version of this, but let's do this. So now it should work really nicely. Let's time it, right? And this should be faster than the previous one. So probably, let's see. Yeah, 100 nanoseconds. I mean, so basically it's basically cache lookup, right? It looks okay, 35. So let's do 45, right? It should be, well, it says 99 seconds. How can it go down? Well, remember it's plus minus 2080 nanoseconds. So basically, it's only had to do, assuming we didn't do any work before, a cache, we could maybe have cleared the cache, but only had to do the value calculations for last 10 items, 45, 44, 43, 42, up 35, right? Because we already have all these items already done, right? So pretty nice. I mean, it's almost like, almost no work whatsoever, right? Because computers are very fast. Adding, of course, so 90 seconds basically, right? So you went from having, exponential complexity to something which is obviously looks linear for sure, right? Because it's almost not increasing. It's probably not log n. It can't be log n because of course we have more items, we have to do more work, right? So, but the potential, of course, if you are doing the same calculation that you did before, it's just lookup, right? It's just, that is all one then, basically. I just look up then, right? If you do something, if I look for a calculation for Fibonacci of 20, right, it's going to be in a cache, right? It's going to be in a cache, you just look it up, basically. And of course, this principle of caching is used everywhere in computer architecture, right? In your CPU itself as well, right? There's 4 levels of caching, right? Because, hopefully the value you want is close to the CPU main arithmetic unit, but maybe it's in register, maybe it's in level 1 cache, and so on, going up to how many levels of cache we have in modern CPUs? How many? Any idea?
Isn't there like 4?
Yeah, well, if you buy the AMD 3XD chip, they have 4 levels, right? Normal CPUs, just pretty much everything else has 3 levels, L3, right? So that's why the X3D chips are so nice for gaming and things like that, because they have this extra level of caching, this 4th level basically, right? So they get slower, right? Eventually you get to main memory, right? That's slower, right? You start with level 1, which is really fast, right? Latency, right? Very quick to get the data out. So level 4 actually sits on top of the CPU actually, right? It's 3D, right? It's like a level, right? So there's a downside. So what's the downside to this? You have this 4th level cache sitting on top of CPU. Does anyone know? I said later. Yeah, it's slower, but it's also it's quite a bit. I think it's like megabytes. Yeah, it's megabytes, right? But there is a side effect for those who explore buying these chips. You know what's the side effect? What's the limitation of them? They're very fast, but there's one downside to this. If you put forced level cache on top of CPU.
Doesn't it throttle the CPU?
Yes, exactly. It affects the heating and the cooling because you can't overclock them that well. Actually, you can't really. I think they're limited to overclocking at all. Right. So if a regular CPU is not treated just regular flat, you can overclock maybe 6 gigahertz or something like that, right? But these 3D, those who have 3D cache, then I think they go to 5, roughly about 5 gigahertz, or maybe something like that, right? Yeah, something like that, right? Yeah. So, but they have a limit. Basically, they start overheating, basically, right? But the trade-off is worth it because you have this extra level of caching, right? Which is quite a bit. It's relatively close to CPU. It's obviously closer to CPU than the memory, which sits on a bus, right? Somewhere a couple centimeters away, right? So, a couple millimeters or centimeters. It makes difference with light speed, right? So, big difference, basically, right? So, okay, but I digress, right? So. We see here, so this idea of caching is everywhere, pretty much anywhere in computer industry, pretty much anything, right? When you index something, right, in databases, I mean, it's everywhere, right? So here we get this free win, right? So I checked, all right, so my solution was 90. Let's do this, the one I did myself is 20. So twice as slow, but still pretty fast. My solution, right, without this factory optimization, right, is about twice as slow, but still pretty decent, usable, right? So, yeah, so nice to know. What else? What else you want to see? Right, I can do play around, Fibonacci. Right, I can get as big as numbers as I want. Can I do 2000? Yeah, right. Okay, but yeah, so of course Fibonacci, of course, because it's nice to do. Can I do 5000? Can I push it? Yeah, I can do 5000. Right, yeah. So there is one problem, of course. With top-down memoization, the only problem is that theoretically you can hit the stack, the limit for recursion, because you still have recursive calls, right? So I set to 10,000, right? So I'm not hitting the problem here, right? But theoretically, right? Well, it's not the caching problem, but it's actually the recursive calls problem, right? And again, in production, recursion is seldom used, right? So obviously here, well, we'll take a break, but I think you know what we could do, right? I mean, here we have a regular solution for Fibonacci, of course, would be the linear solution using just a regular loop, right? Yeah, and that's going to be good too, right? So, let's see, 944. Do we want to check? We can, of course, we're going to basically use a bottom-up method. So that's going to be our next method, right? That's typically a looping solution, right? We don't worry about stack, right? I will not worry about the recursive calls. So here, of course, Fibonacci, it's going to be just a loop, and you'll need to store some values, right? And here it's trivial, right? For Fibonacci, it's easy, right? We're going to be storing the previous two, basically, right? And that's it. I mean, as simple as that, and that's classical dynamic programming. But okay, we'll do this after the break, and I'm sure you can play around. You can make your own solution. That's like 1 minute, make a loop, right? But let's continue at 10 o'clock, right?